Welcome in the second lecture of Digital Signal Processing. I'm Dr. Abdulrahman Qasim from Majma University. Today we will talk about discrete time systems, convolution, and cross-correlation. The block diagram of a digital signal processing system is represented here. As you see, we have an analog input signal or continuous time signal. This is our analog to digital converter. The purpose of this converter is to convert our analog signal into digital. This is a digital input signal, as you see, and this is our digital signal processor. The digital signal processor has its own response to this input, and we will have our digital output signal. After that, after finishing, we can convert again our signal from digital to analog in order to have our analog output. Of course, because of the implementation of digital signal processor, the analog output signal will be different from the analog input signal. This is a very basic block diagram of a digital signal processing system. Example of a discrete time system, we have x of n equals the absolute value of n from -3 to 3, and 0 elsewhere. This is our input x of n signal, and this is our output. Really, this is the system that we have. The input, this is the output. What is the output here? The output here is 1 over 3 x of n plus 1, x of n, and x of n minus 1, which means we have 3 samples. Sample at the origin, no shifting. We have one sample is shifted to the right with amplitude equals 1, and we have a sample shifted to the left by 1, and it is multiplied by 1 also. All 3 samples, they are multiplied by 1 over 3, which means we have 3 samples. Every sample will be as input for our system to have y of n. Moving the average filter, for example, this is the solution, as x of n equals 0, 3, 2, 1. This is 0, 1, 2, 3. This is the input x of n, and this will be our output for n equals 0. So as I said, we will make an input for all of n that we have. So if this is our x of n, and we take 0, which means y of 0 based on this system, this is our system, the y of 0 equals 1 over 3 x of minus 1, because we have n equals 0. So we have x of minus 1, x of 0, and x of plus 1. So the result will be 1 over 3, 1 plus 0 plus 1. From where? Because x of minus 1 we have 1, x of 1 we have also 1, and at 0 we have 0. So 1 over 3 multiplied by 1 plus 0 plus 1 equals 2 over 3, and this is based on our system. What we can see, for input 0, we will have 2 over 3 for input 0 as x of n equals 0. Our output as y of 0, we have 2 over 3. But remember, in order to find only one input, we had to use this system for 3 samples. So this is the response of the system to have the output, and this is our input data. This is y of n in general. As you see, we find only for 0. Now we have to find for 1 and for minus 1. If we will put 1 here, so we will have, as you know, for 1 we have x of 2, x of 1, and x of 0. And x of 2 we have 2 from here, and x of 0 we have 0. 2 plus 0 equals 0, and we have x of 1 we have 1. 2 plus 1 equals 3, and x of 1 minus 1 will be x of 0, which is 0, and we have 3 over 3, and we will have 1, which is here. As you see, we have 1, and so on. We can find for all inputs our output based on this system. If we change this system and the input is fixed, of course our output will be changed, because the system or the discrete time system is changed. And this is another example. The previous example, we used the system as a filter. Now we are using another system we call Accumulator. As you see, we have another system. It is accumulator, x of n plus x of n minus 1 plus x of n minus 2, and so on. N equals from minus 3 to 3. So we will take only these values. As you see, 1, 2, 3 minus 1, 2, 3 plus. Other values above 3 or below minus 3, they equal 0. As you see here, this is our solution. We will use this system as accumulator, and we will this is our output. From where, for example, if you want to know from where we have 6 here, as you know, this is based on y of 0, and y of 0 here means x of 0, which is 0, plus x of minus 1, which is 1, and x of minus 2, which is 2. 2 plus, as you see, we have to sum this at 0, and we will have 6 here. Okay, so we have 3 values: x of 0, x of 0, x of minus 1, and x of x of 0. At 0 we have x of minus 1 and x of minus 2. So if 3 plus 2 plus 1, we will have 6 here. So this is the idea. Now, classification of discrete time systems. There are different classifications of discrete time systems, but the main classification, there are memoryless systems. In this case, if the output of the system at an instant n only depends on the input sample at that time and not on past or future samples, then the system is called memoryless or static, which means doesn't depend on previous values, and there is no need to have a memory to store previous data. It depends only on current data and future. Also, we have example: y of n equals ax of n plus bx square of n. You see, there is no negative values here. It is depends only at an instant n only, n, at current time, at present time. Otherwise, the system is said to be dynamic or to have memory. If n will have n minus 1 or n minus 2, means this system is not memoryless system. It is a dynamic or have a memory. For example, this system, as you see, n minus 2 means the system is shifted and depends on previous past value, or if it is plus, it based on the future value, and it will not be a memoryless system. It will be dynamic or memory system. There is also what we call causal non-causal systems. In a causal system, the output at any time n only depends on the present and past input. See, n depends only on the present and the past, but not on the future, and this we call causal system. An example of the causal system, as you see, y of n equals the f, or maybe it is this, the Fourier transform x of n minus 1, x of n minus 2, and so on. And all other systems are non-causal. If we have plus here or any shift to future values, means the system is non-causal. And a subset of non-causal systems where the system output at any time n only depends on future inputs is called anti-causal. Anti-causal, we have future, only future, which means we have anti-causal system. But if we can mixed have minus and plus, past and future, it will be non-causal. So in this case, we have 3 types: causal, non-causal, and anti-causal. Stable versus unstable systems. Unstable systems exhibit erratic and extreme behavior, which means we have what we call a bounded input, bounded output. Is stable systems that are producing a bounded output for every bounded input. This is an example of a stable system. As you see, y of n equals y squared n minus 1 plus x of n. That is stable or unstable. Let's make a check. X of n, c delta function of n is a bounded signal. If this is a bounded input signal, which means we have c is here a constant scalar value, so we have delta of n, and every time y of 0, let's see, we will use this system and we want to check it is stable or not. For x0 we have square, as you see, this is the function x of n, and this is our x of n. We will have x of n here, c delta function of n, and this is y squared of n minus 1. So y of 1 equals c squared, y of 2 equals c to the power of 4, and y of n equals c to the power of 2n. This is the output for this system based on a bounded signal input, which means c is up by increasing the system and the power, the system goes to infinity, and if it is goes divergent, we have a divergence here to infinity, which means the system is unstable. And we have linear versus non-linear systems. This is superposition principle. If we have a system to transform two input signals, summation of two input signals, every input is multiplied by a constant or a scalar value. So we can distribute this transformation over every input separately, which means if I have this transformation or a system to transform two inputs to sum the inputs, after that make transformation, it is the same to make transformation for every input separately, and after that we can sum them. This is the system f, this is the system then. This is f x of n, we have y of n. If we have kx of n, so we have ky of n. This is a scaling property, which means if we have a system with output y of n, if you multiply the input by k, it is the same, you can multiply the output by k, which means the constant doesn't have any effect on the system. This is f and f. This x1 we have y1, x2 we have y2, which means x1 of n plus x2 of n as two inputs of this system. We have y of n plus y of n separately. We call this additivity property. So this is some of the linearity of our digital systems. A relaxed linear system with zero input produces zero output. Let's have an example. Y of n equals x of n squared. This is linear or non-linear. The solution, y of n equals x1 of n squared, and y2 of n equals x2 of n squared, which means we have two inputs. y3, it is the transformation of the system for these two inputs. This is the superposition property, and I can make this for every input separately to have output, y1 for the input 1 and y2 for the input x2. This is the second input. So they are linear. Why linear? Because they are the same. As you see, this is the same as here. Another example, y of n equals exponential x of n. Is linear or non-linear? Useful hint: in a linear system, zero input results in a zero output, but in this case exponential of 0 will give 1, which means this system is non-linear. X of n equals 0 means y of n equals 1. This system linear. This is a very simple hint to check the system linear or not. Time invariant versus time variant systems. If input output characteristics of a system do not change with time, then it is called time invariant or shift invariant, which means it doesn't depend on time. And this means that for every input x of n and every shift k, as you see, x of n, this system transforms x of n to be y of n. Then in this case, if we have x of n plus s, the system y of n plus s, which means this system is time invariant. we shifted by time, but this will affect our input, and it is the same shifted by time. So x of n, y of n, x of n minus k will yield y of n minus k. Time invariant example differentiator. You see x of n, the system to transform differentiation. X of n give y of n equals x of n minus x of n minus 1. This differentiator, see minus, and this is difference shifted by 1. This is x of n minus 1 will, after transformation, will give y of n minus 1, will give x of n minus 1 minus x of n minus 2. And this is an example of time invariant example. See, I have shift here, I have shift here. So x of 1 give y of n minus 1, and this is the same n minus 1 minus 1 minus 2. If this input shifted by 1, see, so y of n will be shifted also by 1, which means it is a time invariant example. But for time variant example, for example, modulator. The modulator x of n, this is a modulator to transform x of n to be y of n using the modulator. X of n cosine omega naught t. If we have x of n minus 1 and we make a modulation, we will have x of n minus 1 cosine omega n. This is a modulation, and in this case we will have y of n minus 1, x of n minus 1 cosine omega n minus 1. You see, we have here n minus 1. If you will make 0, input cosine is 0 will give you 1. It will not give you 0. This is also n minus 1. It will give you, now it depends on time, depends on n. This is input, and this is input. This is input, and will give you output. Shifted here, we have the same shifted in time here, but shifting an x of n minus 1 here, make shift here in the time. So now it depends on time, so it is time invariant system. A linear time invariant system, which means it has the three properties at the same time. So we have a system linear, this is a time invariant system, and maybe there are other properties, but the linear time invariant systems have two important characteristics. First, time invariance, and we explained this before, and the linearity. System T is called linear if it satisfies this property as we discussed before. Why do we care about only linear time systems? Why? Because the availability of a large collection of mathematical techniques, many practical systems are either linear time invariant or can be approximated by linear time systems, which means we are interested in linear time systems because of their wide application. What is the impulse response of the LTI systems? The impulse response, as you know, h of n is the impulse response of the system in the time domain. So the response of the LTI system to the input unit sample delta function, this is the transformation by the system of the input delta function, is we call the impulse response. So this is my delta function, this is my impulse response using this linear system. So converting, transforming delta function to have impulse response using this linear system. Why delta function? Because in impulse response we are working with every sample separately. So every sample can be represented by what? By delta function shifted to the right or to the left. So an LTI system is completely characterized by single impulse response h of n, which is basically based on the delta function. If I have x of n with linear system, this is the impulse response of the system, I will have y of n. So y of n is the linear, is the result of transformation of the input based on the linear time system. This is the the general equation, as you see, from k minus infinity to infinity. This is our input, and this is our impulse response, which is h of n minus k, and we call this the convolution. So the convolution between the input and the impulse response will result or give the output y of n. So response of the system to the input unit sample sequence at n equals k, and we have the convolution sum of these two signals. And as you know, in the time domain, the operation that represent the changes of the input to have the output based on the impulse response, we call convolution. Computing the convolution sum, this is our convolution, and as you know, to make convolution, this is an example, we need at least 4 main operations: reversing or folding, shifting and multiplying, repeating for all n0, after that summation. So this is an example of shifting, multiplying, and summation in order to have the output. And we will not discuss the convolution in details, because I think you know about this technique or operation in continuous time signals. What are the main properties of convolution of linear time invariant systems? This is a commutative law, you know this. We have a distributive law. You see, I think it is clear. For example, for commutative law, if I have x of n as input, this is the impulse response of the system. I have y of n. This is if I put the impulse response as input and the input as impulse response, I will have the same result. Distributive law, which means if I have two parallel input x of n, is applied to two parallel impulse responses, I can sum the result and have y of n. It is the same if you sum the impulse response first and apply the input to have the output. This we call distributive law. We have associative law. This is the associative law, as you see. In this law, we have two impulse responses in sequence or in cascade form. As you see, we can multiply. We have convolution, by the two impulse responses, and after that we can apply the input to have the output, or we can first apply our input to the first impulse response, and the result output of the first impulse response of the first order of the first system can be applied to the second impulse response to have the final y of n. And this is also, as you see, I think it is clear, it is mixed between the first and the second clause. See, this is the input first, second. This is the same as above, but in this case, as you see, x of n can be applied, and you see I change only the places. So if you will apply your input to the second impulse response or to the first impulse response, it will be the same. What are the properties of the linear time invariant system? Causality in linear time system, we already discussed this, about the causal linear time invariant systems. And causality in linear time systems, this is an example, and this is the proof of this causality and the stability of the LTI system for a bounded input, bounded output, also we discussed before. And in this case, the LTI stability is translated to a condition on the impulse response too, and LTI system is stable, and if it is impulse response is absolutely summable. And this implies that the impulse response goes to 0 as n approaches infinity, and this is a very important property of the system to be stable, because if the system will approach 0 when n or h of n when n goes to infinity, means the system stable, otherwise the system will be unstable. This is the stability or condition of the system as we discussed, and this is also our for linear time invariant system, it will be stable sufficiently if it will apply or will satisfy this condition, and necessity let us assume that S of h equals minus infinity. Take the input with values. This is for the values, and we have y of 0 S of h, which is unbounded input, which means the system is unstable. This is an example about stability. As you see, this is the impulse response. The impulse response for n positive equals 0 and positive values, it is a to exponential n. If n less than 0 or negative values, it will be b to the power of n. A and b, which means the system stable or not. We have a solution. This is our absolute value h of n. As you see, this is for positive values, this is for negative values from the impulse response. After that, we have this, after calculations, we have beta equals 1 over absolute value, we're assuming this value, and finally we have beta over 1 minus b, which means b less than 1 or absolute value of b more than 1. So in this case, if will be approaches 0, means the system is stable, and based on beta, it will be approaches infinity, which means the system is unstable. So the system can be divided into two types based on their impulse responses. For example, a finite impulse response system has finite duration h of n, and which can be written or can be represented using this equation for k equals 0 to m minus 1, and this case n is implies that m, if m equals 0, we have about positive values. This means that the output at any time n is simply a weighted linear combination of the most recent m input samples, which means the finite impulse response of the system has a finite memory of length m. For infinite impulse response system, which has infinite duration h of n, so it is output based on the convolution formula becomes causality assumed for this equation, and in this case the weighted sum involves present and all past input samples. Thus the infinite impulse response system has infinite memory. Discrete time signal system described by difference equation. How we can represent our systems? Of course, the only way is to use the difference equation. Finite impulse response systems, we'll talk about their design with infinite impulse response later. They can be readily implemented by their convolution summation, involves addition, multiplication, and finite number of memory locations. The infinite impulse response system, however, cannot be practically implemented by convolution, as this requires infinite memory locations, multiplication, and additions. As you know, for convolution, we have 3 main operations, or 4, reversing, multiplication, and addition. And this is for limited input durations or data. It will be, we have a specific or limited memory, but for infinite impulse response, it will be difficult or practically cannot be implemented it requires infinite memory locations. However, there is a practical and computational efficient means for implementing a family of infinite impulse response systems through the use of difference equation. Difference equation, they are limited by samples and can be used. Example of a difference equation. A cumulative average system, as you see, this is our system. Y of n equals 1 over n plus 1. This summation from k equals 0 to the nx of k. This is accumulator or accumulator with average. We make a cumulation and divided by n plus 1, which means I make accumulation or cumulative average system. Y of n minus 1 shifting, as you see, will give 1 over n because minus 1 plus 1 equals 0. And this will be equate from 0 to n minus 1, x of k, and n equals 0, 1 to n minus 2, based on number of samples on our difference equation. and so on. N plus 1 y of n, it is multiplication, and we have finally that this is our y of n equals n over n plus 1, y of n minus 1 plus 1 over n plus 1, x of n, and so on. This is about the difference equation, how we can represent the output based on the input. This is the feedback values, and we have initial condition. The initial is important because if you start your system, you need initial conditions when n equals 0. Cross correlation, or the cross correlation concepts, means that we have to transmit and to receive two signals, and these signals can be compared between each other, and to show the similarity between these two signals using the cross correlation concept. This is the transmitted wave. As you see, it is a good clear waveform, and this is the shifted version of the transmitted waveform plus noise. After receiving, as you see, the signal or the waveform is shifted to the right and is distorted by noise. So I want to know what is the similarity between these two signals. By idea, these two signals should represent the same information or the same signal. So through the cross correlation between the transmitted and received signals, it will be an efficient way to measure the degree to which two signals are similar to each other. So this is the idea, this is the basic, the transmitted, this is the shifted with noise. So cross correlation is a mathematical operation that resembles convolution. It measures the degree of similarity between two signals. This is a visual demonstration. This is the test signal of the shifted distorted signal x of n. This is the cross correlation machine. We have different inputs and different outputs that can be summed based on number of samples, and this is the y of n. As you see, this is our input and this is our output of the cross correlator, cross correlation means that we comparing two different signals to know the degree of similarity between them. The amplitude of each symbol in the cross correlation signal is measure of how much the received signal resembles the target signal at that location. The value of the cross correlation is maximized when the target signal is aligned with the same features in the received signal. This is x of n, this is y of n. Really, if we have the signal as the same, the transmit and received, or the two signals, they are very, very similar. The output will have another ideal output, which we call will be with other properties like using the cross correlation to detect known waveform is frequently called match filtering. So what is the difference between match filter and cross correlation? In match filtering, as you know, the impulse response of the system is the reverse version of the input signal, and this is which means we are comparing two similar signals between each others, and they will give us the maximum value at the output, which means, in other words, the energy of the input signal. But in the cross correlation, we are comparing two different versions of signals. The input is different from the impulse response, and so we call this cross correlation. Applications include radar, sonar, biomedical signal processing, and digital communications. This is applications of using the cross correlation. Mathematical definition: this is x of n. This is the transmitted desired signal. Y of n equals ax of n minus d. This is the effect of delay, and this is maybe effect of frequency, the effect of noise, and mainly it is the additive Wadhwson noise. So this received the signal attenuation factor, this additive noise, and this is the delayed version of the input, and this is the version of the output of the cross correlator to compare between x and y. and see this is our output. This is the cross correlation x of n and y between them. So the maximum correlation will be 1 or minus 1. If they are similarity 100%, which means they are the same, we have 100% correlation. If they are orthogonal, we can have 0, and if they are the opposite or what we call antipodal, they will have cross correlation maximum but in negative value. Calculation of cross correlation. Cross correlation involves the same sequence of steps as in convolution, except the folding part. So it is the same as convolution, but we don't have to reverse this one of the signals before shifting summation, multiplication, and summation. So basically, the cross correlation of two signals involves shifting one of the sequences, multiplication of the two sequences, summing over all values of the product. Cross correlation versus convolution. The cross correlation machine and convolution machine are identical, except that in correlation machine this flip doesn't take place and the samples run in the normal direction. So this is the cross correlation in non-commutative. As you see, this is the convolution between x and y. Will have this result. Convolution is the relationship between systems input signal, output signal, and the impulse response. Correlation is a way to detect a known waveform in a noisy background. The similar mathematics is only convenient constants. Autocorrelation is we have this is autocorrelation, which means we have to compare two the same signals, or the signal with itself, but delayed by L. If there is no delay, which means x of n multiplied by x of n, we have the maximum value as the energy of this signal. The more delay maybe will yield to decrease the value until we have 0. Of course, this means shifting to the right and shifting to the left. It's the same as convolution, and we have maximum value in positive and maximum value in negative based on these two signals. But you have to know these signals, they are because they are the same, and after convolution, after correlation, you will see that our output, this is the output of correlation, we have see the similarity and they are identical around the y-axis. Properties of autocorrelation cross-correlation sequence. It can be shown that this is about the energy of x and energy of y. This is for if we have the autocorrelation of x, we have energy of x. If we have autocorrelation of y, we have the energy of y. And for autocorrelation, we have this is the autocorrelation. This is the absolute value of the autocorrelation for x, less or equals the autocorrelation of 0 at a, which is the E of x. This means that the autocorrelation of signal attains its maximum value at 0 lag. Makes sense as we expect the signal to match itself perfectly at 0 lag. Of course, at 0, the signals, they are matching, they have the same, no delay, and they have the same values, so it will give you the maximum of multiplication when there is no shifting. If signals are scaled, the shape of the cross correlation doesn't change, only the amplitude are scaled. So it is often desirable to normalize the autocorrelation and cross correlation sequence to be ranged from -1 to 1. 1 if they are indeed identical with zero shifting, and also -1 will be with 0 shifting, but they are antipodal signals, or they have phase shift 180 degree. This is the normalized autocorrelation. How to normalize this? Easy. You will take all the signal. All the signal will be divided by one maximum value. So if you have the maximum value is 5, the maximum value, so the signal will be divided by 5. If you have in the signal maximum 0.5, so the maximum will be 5 over 5, which means 1. So the maximum value will be 1 or minus 1. And this is the normalized cross correlation. This is auto because we are comparing signal with itself, and this is for cross correlation because we are comparing here signals with another signal. But these values for these two signals as autocorrelation at value equals 0. Thank you for listening, and see you in the next lecture.